Okay, next speaker is Ross Wakefield. And apologies, initially I announced the wrong affiliation for him. He is from Bristol University, and he will talk about photonic quantum simulations of coupled PT-symmetric Hamiltonians. So Ross, please go ahead.
Okay, hi. So I'm Ross Wakefield. I'm a student in the Quantum Engineering Center for Doctoral Training and Quantum Engineering and Technology Labs, CAT Labs, in University of Bristol. I'm supervised by Anthony Dang in Bristol and Yogesh Yulahekar in IUPEI. So this project there's maybe about a dozen people involved in total, but most recently, over the past few years, Nicola Maraviglia and Patrick Yard have taken experimental data, and I've been working on theory. So this is on photonic quantum simulations of coupled time-reversed PT-symmetric Hamiltonians. But before I start, I'm going to go through the order. Essentially, in the lab, we have a photonic interferometer that implements some unitary transformation. So I'm going to talk about that first to motivate where this comes from, because most methods of simulating p-symmetric systems using dilation involve Hamiltonian dilation, but we use unitary dilation instead, which is motivated by the fact that we use a photonic unitary chip. So we apply this method of unitary dilation to essentially a non-unitary matrix, which in this case is an exponential of a PT-symmetric Hamiltonian. And then from there, this explains, or we use this to describe coupled forward and reversed PT-symmetric systems. And then into this chip, you can input single photons or multiple photons. So I go through the process of explaining the experiments with a single photon and experiments and possible future experiments with multiple photons, and how you can get an interference with single and multiple photons. And then how that extends to the idea of varying distinguishability of multiple photons. And in turn, that is similar to extending a Hong-Mandel effect. So as I said, there are already methods for simulating PT-symmetric and other non-Hermitian Hamiltonians using dilation methods, where so for some n-mode or n-qubit system, you have you embed this into a larger system, and this is generally called dilation. And most people sort of in the past have got sort of three specific randomly chosen methods of dilation, I suppose similar methods of dilation, but they're all Hamiltonian dilation. But in our lab in the basement, we have a photonic chip, which directly implements a unitary transformation. So instead of doing Hamiltonian dilation, we want to go for something a bit more like unitary dilation. So we directly implementing a unitary instead of having to take the Hamiltonian, dilate the Hamiltonian, and then turn that into unitary. We want to go straight from, I suppose, a non-unitary transformation into a unitary transformation on a larger system. And then having done that, we want to see if this works and how it does actually simulate some kind of non-Hermitian system. So in the lab, this is the chip we use specific for this experiment. It's not specifically created for this experiment, but this is the one we use in these experiments. It was described in the universal linear optics paper in Science by all of these authors, and it's a 6-mode Rec scheme. And a Rec scheme is this, it's a triangular shape, and there are various elements. So each of these white lines represents a waveguide on this photonic chip, and you input photons, single photons or multiple photons, into these waveguides. And then you have they're colored in gold here, and these little gold things are phase shifters. So they change the phase of whatever photon is in the waveguide at the time. And then in between these phase shifters, you have beam splitters, and these just act as beam splitters between the waveguides. So there's a lot more detail in that paper, but this is the system that we're using for the experiment. and it's used in quite a lot of experiments we do. But it's a 6-mode Rex scheme, and that means that there's 6 input modes, 6 output modes. So 6 waveguides, and I have many photons through these waveguides. And as I say, that this scheme implements a unitary directly. So whatever unitary we have, we need to figure out a way. There are specific ways of the Rex scheme is a specific way of taking a unitary and turning it into this triangular system of beam splitters and phase shifters. So we have this 6 modes Rex scheme that is a unitary transformation, and we want to use that to create some kind of non-unitary transformation on some subset of that system. So the way we do this is called Halmos dilation, or unitary dilation. There is a paper by Paul Halmos on Halmos dilation, but it's actually pretty difficult to get hold of. So I've just got I often refer to this paper, Julia operators and Halmos dilations, because it's more recent. But the point is that if we first consider a single 2-mode system of a beam splitter, and although there are various ways of making a beam splitter unitary, we take this specific way and then add a few more phases. So we have this beam splitter in the middle, cos theta and I sine theta terms. So this essentially causes interference or coherence between the 2 waveguides. And then at each side of the beam splitter, we have phase shifters. There are extra phases here. So this is kind of superfluous to creating a unitary, but it makes life simpler at a later point. So we create this beam splitter and surround it by phase shifters. And then we extend this idea in 2 modes to an arbitrary number of modes. So here, to n modes. And instead of considering a single beam splitter between two modes, we consider this as a vector. So we have some arbitrary number of, well, some n beam splitters. And these couple the 2 n modes together. And then these phases become unitaries. So this is now a much larger 2n by 2n unitary transformation. And this is essentially Halmos dilation or unitary dilation. This is, in itself, this is maybe not very obvious what it's useful for, except that you now have a big unitary transformation. But to get around this, we want to implement some non-unitary matrix transformation M, and we consider this as a singular value decomposition, but we consider it as a normalized singular value decomposition. So whereas before I had a UA, UB, UC, and UD as extensions to the phases, we now consider UA as a U, cos theta as a normalized singular value, and UB as V dagger. And then that means that we've now implemented a normalized version of the non-unitary matrix M. And this normalization is essentially just the maximum over all singular values of that matrix. So there are a number of options that at this point, because if I go back to this slide, I've left UC and UD unspecified, but for simplicity, I suppose, or just because we can, we take UC and UD and relate them to U and V dagger as well. And then what this does means that we can create a system that's twice the size and it implements transformation M, as well as on the top n modes, it implements the transformation M dagger on the bottom n modes. And then between that, there's this term ID and ID star, which is essentially an interaction term between these 2 systems. And D is given here, it turns out, as square root of I minus M dagger. M tilde is just the normalized version of M, normalized by the maximum singular value. So having done that,
Ross,
yes.
Philip has a question. Philip.
Yes, hold on. Can you go back to the slide with the U2N? Well, go back one more. No, yes. What I don't understand is this. No, that was it. That's the right one. What I don't understand is it seems that this does not work if n equals 1. And yet it does work for n greater than 1.
Okay.
I'm wondering if it's not related to the fact that for SU2, the representations are real, whereas for SU greater than 2, you have complex conjugate representations. So I'm wondering if it's the adjoint of SU2 is real, but the adjoint of SU3 contains complex conjugate. I'm wondering if that's related.
I'm not 100% sure. So for n equal 1, as in is a 2 by 2 unitary, this is, as I say, it's kind of superfluous to what's needed. So it's a unitary, but it's kind of unnecessary. There's an extra unnecessary phase in there.
Oh, I see. Okay.
Yeah. So you could just get rid of one of these phases and say that's not a unitary. But this phase, and it doesn't do any harm. We can physically create this transformation on our chip because it's just, I mean, you won't be able to detect what this extra phase is, but we can still physically create this transformation. It is just a beam splitter and 4 phase shifters on either side. What this means in terms of, I suppose, what's going on is it's essentially just the global, as far as I'm aware, is essentially just an extra global phase that we won't be able to use this global phase to detect, or we won't be able to detect or determine anything about it. But we can still physically implement it and just say, well, whenever you take the modulus squared, we can't tell what it is.
Okay, in that case, what makes the UA, UC, UB, UD guaranteed to be observable in more than 2 dimensions?
Well, again, nothing in particular. I mean, to a certain extent they will be, because there's still, most of the parameters are still required. But again, there can be extra phases. And there's nothing to say that I could create one system in UTN, and I could create another system of UTN. And although they could technically be different systems, the simulation results could in fact end up being the same. And that's...
So what I think you're saying is that for n greater than 1, you have to introduce these UA and UB, UC, and UD.
Yes.
Whereas for n equals 1, you don't need to.
Yeah. I mean, strictly speaking, you don't need to introduce UC and UD for other reasons. And there are other sort of versions of this dilation where instead of, so this is a 2n by 2n matrix, but you could say have a n plus 1 by n plus 1 matrix. And this is also a valid dilation.
Okay.
It's maybe not a Halmos dilation. I'm not sure on that, but it is a valid method of dilating.
Thank you. Thank you.
So hopefully that answers your question. But as I said, going back to the 2n by 2n system, because it's 2n by 2n, we relabel the top n modes as being in a forward system and the bottom n modes as being in a bottom system, or the reverse system. And the reason we do this is, if I go back to this slide, is that in the top subsystem, we implement the transformation M, and then in the bottom subsystem, we primarily implement the transformation M dagger, apart from the fact that there's interactions between these 2 subsystems. And then in the PT-symmetric system that we use, it turns out that this M dagger is just the time reverse transformation of M, so forward and reverse system. And throughout this, because we have a 6-mode Rex scheme, this allows us to implement a 2-mode PT-symmetric Hamiltonian, which we use this, and a 3-mode PT-symmetric Hamiltonian, which we use as this in the forward system, and yeah, the forward system in both cases. So as we can input into our 6-mode Rex scheme, which I've got a diagram here, a photon into the top subsystem, or a photon into the bottom subsystem. And in both cases, I've just said it goes into mode 1 of the forward system and reverse system. And from that, it implements the transformation M on the top 3 modes and ID star on the bottom 3 modes, if you input a photon into the top subsystem. And then if you input a photon into the bottom or reverse subsystem, you get the opposite. So if you then detect it out of the reverse subsystem, you get the transformation M dagger. And if you detect it out of the top subsystem, you get the transformation ID. In our actual experiment, we use a single photon detector. So essentially, you can only detect a single photon from a single mode because we're only inputting single photons at the minute. And doing the experiment and classically simulating what the experiment should do gets pretty close results. There may be a few slight differences, but experimental error. And as you can see for the Hermitian system, it gives straightforward oscillations, and the systems are, the reverse and forward systems are uncoupled from each other. So it's very standard oscillations. It's just the Pauli X Hamiltonian. And then whenever you introduce a non-Hermitian term, I gamma is 0.25, critical point is gamma equal 1. So whenever you introduce this, you get it's periodic, it's still periodic, but you start to see the oscillation kind of changes slightly. And what the output of the second mode decreases in probability. Then we have this thing called a vacuum state. And that's essentially, because it's a non-Hermitian system, and we are simulating a normalized version of that. But nonetheless, this means that everything you get put in doesn't necessarily get detected at the output of the forward system. So we input a photon into mode 1 of the forward system, and it can be detected at the output of mode 1 or mode 2, or neither mode 1 or mode 2. And in that case, we call that the vacuum state. And that essentially allows us to conserve probability. And again, we do see that is also periodic. And again, we can simulate beyond the unbroken regime into the broken regime and exceptional point. So there's not really terribly much to say about this beyond the exceptional point and at the exceptional point. Because it's normalized, it heads towards a steady state value for all three options. And then having done that.
Where was the exceptional point on your picture?
So this graph that's inset is the evolution at the exceptional point.
At the exceptional point.
Yeah, oh. Yeah. It's slightly different too whenever you go beyond the exceptional point, but it's the same kind of idea. Everything just evolves towards a steady state value because it's normalized. So we can take this single photon, and instead of inputting it into a single mode of the Reich scheme, we can now put it into a superposition of modes. And we can even make this single photon mixed or partially mixed, as well as coherent. And this gives kind of different effects. And from inputting this density matrix, where it's in a superposition of first mode in the forward system and first mode in the reverse system, we can introduce this A parameter, which is the amount of, I suppose, how coherent it is. And then from that, we measured the sigma x by the x expectation. And this kind of gives something that's in some sense analogous to some kind of Zitterbewegung effect. So kind of some trembling motion where the forward system is interacting with the time reverse system and giving oscillations. And that's shown here. So in the PT unbroken regime, we do find these oscillations. And these oscillations are maximized whenever the state is most coherent. And whenever we decrease the coherence of the state, we find that these oscillations tend towards 0. But for the broken regime, we just find, again, everything just tends towards a steady state. So that removes these oscillations that happen in the unbroken regime. Although again, in the broken regime, the steady state value is 0. There's just 0 expectation value. And from a single photon, we want to input multiple photons into the system. There are essentially 3 different ways of doing this. And that is that you can input photons into the same mode. So instead of one mode having one single photon, you now have one mode having a pair of photons. So, but this does have some practical experimental issues. We can still do it, but it does have some practical experimental issues. Essentially being that all we have is all we use in that lab are single photon detectors. So the way we measure 2 photons in one mode with single photon detectors involves using an extra single photon detector and adding a beam splitter between them. So this actually reduces the probability of measurement success. So it takes longer to do the experiment, as well as the fact that adding 2 photons also increases the length of time to do the experiment in the first place. So a slightly easier way to do is actually to have 2 photons in, say, the same subsystem, but not in the same mode. And this is essentially modeling multiple excitations of the PT-symmetric system. And kind of a further extension of that is to consider 1 photon in the forward. And then this models interactions between the 2 systems. So this looks like whenever we have 2 photons within the same subsystem, this is essentially what the output looks like. And we can show that the system is still PT-symmetric. If you look at the bottom here, you can see that if you parity swap the inputs and outputs, so instead of having a photon in mode 1 and mode 2, this is now the 3-dimensional system. Instead of having photon in mode 1 and mode 2, you put the photons into mode 2 and mode 3, and simply detect the photons in the parity reversed output. So instead of 1 and 2, 2 and 3, 1 and 3 is 1 and 3, and instead of 2 and 3, 1 and 2. And then you can see from that if you essentially simulate the system traveling forward in time, then that is the opposite to if you simulate the parity reversed. So the parity swapping the input and output gives the time reverse of the output. And we can see that holds for whatever value of gamma we pick in this regime. And then we can go further and say that we input 1 photon into each mode. And we still find that this same idea holds. So if you parity swap the input, the output, that now gives a time reversal effect. So you can see this blue line where the output in this specific graph is 1 photon in mode 2 and 2 photons in mode 3 is the time reverse of the output where there are 2 photons in mode 1 and 1 in mode 2. And then the same idea holds for these other graphs. And whereas comparing that with the Hermitian system, it's just the same. But we want to go a step further than that and have 1 photon into each subsystem. So we have multiple photons over the multiple subsystems, 1 photon in the forward, 1 in the reverse. And if we post-select on the same output as was input, as in not post-selecting on the same modes, but post-selecting on 1 photon being in the forward system and 1 photon in the reverse system, then essentially that gives us a direct transformation given by m tensor m dagger minus the interference terms d and d star. And that can be described by this diagram. So in this case, we have a photon input into mode 1 of the forward and 1 of the reverse system. And we can't determine where the photon is because of standard boson photon statistics. We can't determine whether the photon that was input into the forward system remains in the forward system or went into the reverse system. And similarly, we can't determine whether the photon that was input into the reverse system remained in the reverse system or transferred into the forward system. And then because of that, that causes the d and d star terms to be implemented on top of the m and n dagger terms. And that there isn't any experimental data for this, but this is simulation data. There's no reason to believe that experimental data wouldn't be similar. And again, we have gamma is 0.25 and gamma is 1.1. So unbroken and broken regime. This is just for a 2-mode system. And you see that again, oscillatory is periodic in an unbroken regime and evolves towards a steady state in the broken regime. But from this, kind of, if we look back to here, even with post-selecting on 1 photon being in the top and 1 photon being in the reverse system, this still causes this interference term to exist. So we can ask the question, is there a way to get rid of this? But we can also ask another question, which is, can we make this experimental simulation more realistic by having, say, a more realistic model of photons? But there's a third question we can ask, and that is going right back to the start and looking at what unitary dilation of a single mode looks like, or a beam splitter. And whenever we think about two photons, interference, and a beam splitter, the first thing that comes into the mind of a lot of people, if not everyone who does single photon photonics on chip, is the Halm dip. So that is where we have two photons input into a beam splitter, and they may not, essentially, whenever they're fully coherent with each other, then both photons either go out one mode or the other mode. And this is the Halm effect, the Halm-Mandel effect. But we want to look at this and consider if we can use this to get rid of this D and D star term. So the easiest way to go about that is by considering fully distinguishable photons. And if we use fully distinguishable photons, then we can go back to the idea where if we input a single photon into the forward system, we can detect that post-select on that single photon being an output of the forward system. And similarly, inputting a distinguishable photon into the reverse system, we can post-select on that being output from the reverse system as well. And in doing that, this distinguishes from the case where the photons switch between the reverse and forward systems. And we can use this to get rid of the interference terms, the D and D star terms of the matrix. But
how do you distinguish them?
So there are multiple ways of doing this. One is that, as shown here, they're literally different colors. So they're different frequency photons. This is actually slightly more realistic, or well, partially distinguishable, which I'll talk about in a couple of slides, is a more realistic model of photons than fully indistinguishable photons. Another way of doing it would be to time delay the photons. So you have a photon wave packet, and then with some time delay, you have a second photon wave packet coming in. So those are kind of the two most common ways that I would use. I think this notation is, once you figure out what's going on, perhaps is easiest to explain in terms of a time delay. So as I said, we have partially distinguishable photons is sort of the extension of this. Instead of having one discrete indistinguishable and another discrete distinguishable photons, you can consider a kind of continuous regime where the photons are instead partially distinguishable. And we can do this by having, say, some kind of time delay. So we have two photons, and for a simple two-mode system, you can consider one photon being in the top system and the other photon being in the bottom system. So whenever they are indistinguishable, they both arrive at the same time. So in this case, this is described by left arrow, where they arrive at, say, the later, you have two time modes, and in the left arrow, they both arrive at a later time. But if they're fully distinguishable, then that means they arrive at completely different times. So there's no overlap of any wave function. And that can be described by one photon arriving in an earlier time bin and one photon arriving in a later time bin. This is a slightly unusual notation. It's described in this paper, Discriminating Distinguishability, by Stasia Stanisic and Peter Turner. And essentially, this notation describes this this earlier and later time binning idea, or any other variant of distinguishability, where when the top mode is top, whenever the photon is input into the top mode and later time, it's in the left, and whenever it's input at an earlier time, it's in the right. And in full detail, that's better written as the symmetric state, because boson statistics, of the top left and bottom right photons. And similarly, the indistinguishable state is the symmetric state of top left and bottom left. And then whenever you write this out in full, this essentially gives for the indistinguishable state, you can't determine which photon is in the top and bottom modes, whereas for the distinguishable state, you can, which is exactly what we're looking for and makes sense in terms of what distinguishable and indistinguishable mean. So the partially distinguishable state is now written as the input state, some alpha times the distinguishable state, plus some beta times the indistinguishable state. And then from this, the overall transformation is given by the two photons being input into the unitary is U tensor I and I acts on these, we call these label modes, the early time and date time, say, a tensor U, again, tensor I, again, acting on label modes. And then from that, we kind of determine that this is the overall transformation these photons are being acted on in terms of how we're inputting one into the forward system and one into the reverse system. And similarly post-selecting on one being output of the forward and another being output of the reverse system. And that's described by this projector, which is essentially you detect one photon in the forward system, and that photon has some label mode L, and you post-select on the second photon being output of the reverse system, and it doesn't matter what label mode it has. And then from that, you get the output state is the symmetric state of the initial full unitary, M tensor M dagger minus D tensor D star, times the indistinguishable state, plus beta times the symmetric part of M tensor M dagger times the distinguishable state. And this is essentially the sum of the indistinguishable part plus the distinguishable part. And that essentially causes our original transformation, M tensor M dagger, which is the coupled PT-symmetric Hamiltonian evolution, minus some alpha times this interference term on the indistinguishable state. So in essentially varying the strength of how distinguishable the states are, we can vary the strength of the coupling between the two systems, although it comes at the cost of decreasing the chance of essentially post-selection success. So having done that, we can vary this parameter alpha from just arbitrarily setting it to be real for simplicity. We can vary the strength of alpha between fully distinguishable and fully indistinguishable. And we find that simulating in the unbroken regime, or indeed the broken regime, find that simulating it for some time, there is a difference. I find 3D graphs slightly hard to read. So on the right, there is a 2D cross-section of this 3D plot at t equal to 5. And this shows the parameter alpha indeed does have some kind of effect on the state, or well, in what you're simulating with the same input. So to conclude, there are different forms of unitary dilation are possible. Indeed, different forms of dilation are possible. One option of these, the one that we picked, it gives coupled time reverse systems, although you can pick others which are just coupled systems evolving in the same direction in time, or completely different options. And we get from this the usual differences between PT broken and PT unbroken regimes, and the exceptional point for a normalized system. And then we can also have interference between these two systems with either a single photon or with multiple photons. And we can vary the distinguishability to get something that looks like some kind of PT-symmetric extension or non-unitary extension to a Halm dip. And in full, at the bottom, I have a full list of everyone who's been involved in this project since the beginning. Thanks.
Thank you very much.
Thank you very much.
Philip has a question. Philip.
This is a really minor question. When you showed the paper by Huang, Wu, and Mandel, I started to read it. Could you put it back a second? I have a question about what I read.
This one?
Yes. What do they mean by a fourth order interference technique? Seems a very strange concept. A fourth order equation, I understand, but what's a fourth order interference technique?
That is, well, I mean, I don't know exactly what they mean by that. It's been a long time since I've read this paper, but what they do is they take the two photons and they have some, you essentially you split the wave packet, but you don't split the wave packet. You have a wave packet and then you detect the wave packet, and there might be some time delay between these two wave packets. And essentially, whenever you detect with a single photon detector with some kind of time, you measure the correlations between the two photons within some given time bin. And I can only assume that their fourth order interference has something to do with this time bin.
Well, does it mean that you can describe the interference by a fourth order equation? A fourth order derivative equation?
I'm not sure on that.
Okay. Well, I mean, I'm not asking the question completely idly. Fourth order equations are able to give dissipation without having dissipative terms in them. And that was why I was a little, that's what caught my attention here. But I don't know how it works in this particular case.
They might mean, so because they use SPDC, as in parametric down conversion, this is like to create a single photon with this is, say, a second order effect.
Yes.
So if you were creating two photons from this, you need to do this twice. So maybe that's what they mean by a fourth order effect.
Well, that's what I was thinking, because that's exactly the historically, that's the Pais-Uhlenbeck fourth order oscillator. It works exactly that way. That's why I was thinking there might be a connection. Anyway, it's fine.
Then yeah, I don't have a good answer. Sorry.
Maybe one last question. We are a bit over time. No more questions. Then Ross, thank you very much. Thank you.